Artificial intelligence goes for beginner by knowledge and information. In this video we are discussing about Part 4. Machine learning. What is machine learning? Part 2. Machine learning is a dynamic and rapidly evolving field, with ongoing research and advancements. It offers powerful tools and techniques for analyzing complex data, making predictions, and automating decision-making processes. By leveraging the power of machine learning, organizations can gain valuable insights, optimize processes, and make informed decisions in a wide range of domains. Here are a few more concepts related to machine learning. 1. Overfitting and underfitting. Overfitting occurs when a machine learning model performs well on the training data but fails to generalize to new, unseen data. It happens when the model becomes too complex and captures noise or irrelevant details in the training data. Underfitting, on the other hand, occurs when a model is too simple to capture the underlying patterns in the data, resulting in poor performance on both the training and test data. Balancing between overfitting and underfitting is crucial for building a model that can generalize well to unseen data. 2. Ensemble learning. Ensemble learning involves combining multiple individual models, often referred to as base models or weak learners, to create a stronger and more robust model. The idea is that by leveraging the collective knowledge and diversity of multiple models, the ensemble can provide better predictions or decisions. Common ensemble methods include bagging, e.g., random forests, boosting, e.g., ADA boost, gradient boosting, and stacking. 3. Neural networks and deep learning. Neural networks are a class of machine learning models inspired by the structure and function of the human brain. They consist of interconnected nodes, or artificial neurons, organized into layers. Deep learning is a subset of neural networks that involves models with many layers, enabling them to learn hierarchical representations of data. Deep learning has achieved remarkable success in various domains, such as computer vision, natural language processing, and speech recognition. 4. Unbalanced data. Unbalanced data refers to a situation where the distribution of classes or labels in the dataset is highly skewed. One class may have significantly more examples than the others. Dealing with unbalanced data is a common challenge in machine learning, as the model may be biased towards the majority class. Techniques like resampling, e.g., oversampling or undersampling, using class weights, or employing specialized algorithms can help address the issue of unbalanced data. Five. Transfer learning. Transfer learning involves leveraging knowledge and learned representations from one task or domain and applying them to a different but related task or domain. Instead of starting the learning process from scratch, transfer learning helps to accelerate learning and improve performance, especially when the target task has limited labeled data. Pre-trained models, such as those trained on large-scale datasets like ImageNet, are often used as a starting point for transfer learning in computer vision tasks. 6. Model interpretability. Model interpretability refers to the ability to understand and explain how a machine learning model makes predictions or decisions. Interpretable models are important in fields like healthcare, finance, and law, where transparency and explainability are required. Techniques like feature importance analysis, model-agnostic explanations, and rule extraction methods can help shed light on the inner workings of complex models and provide insights into their decision-making process. These concepts provide further insights into the different aspects of machine learning and its application in solving real-world problems. As the field continues to advance, new techniques and approaches will emerge, enabling even more sophisticated learning and decision-making capabilities. Here are a few more concepts and considerations related to machine learning. 1. Hyperparameter optimization. Machine learning models often have hyperparameters, which are parameters that are not learned from the data but need to be set manually before training the model. Examples of hyperparameters include the learning rate, regularization strength, number of layers in a neural network, or the depth of a decision tree. Hyperparameter optimization involves finding the best combination of hyperparameter values that maximizes the model's performance. Techniques like grid search, random search, and more advanced optimization algorithms like Bayesian optimization or genetic algorithms can be used for hyperparameter tuning. 2. Feature selection. Feature selection is the process of identifying the most relevant and informative subset of features from the available data. It helps to reduce dimensionality, improve model efficiency, and mitigate the risk of overfitting. Feature selection methods can be filter-based, using statistical measures, or correlation, wrapper-based, using the model's performance as a criterion, or embedded. Features are selected during the model training process. The goal is to retain the most relevant features while discarding redundant or irrelevant ones. 3. Data pre-processing. Data pre-processing is an essential step in machine learning that involves cleaning, transforming, and normalizing the raw data to make it suitable for training a model. This may include handling missing values, dealing with outliers, scaling numerical features, encoding categorical variables, and splitting the data into training and test sets. Proper data pre-processing ensures that the model receives high-quality input data and can learn effectively. 4. Model deployment. Model deployment is the process of making a trained machine learning model available for use in real-world applications. It involves integrating the model into a production environment, setting up the necessary infrastructure, and creating an interface for inputting data and receiving predictions or decisions. Deployment considerations include choosing the right deployment architecture, on-premises, cloud-based, edge computing, ensuring scalability and performance, and implementing proper monitoring and maintenance practices. 5. Continual learning. Continual learning, also known as lifelong learning or incremental learning, is an area of machine learning that focuses on the ability of models to learn from new data over time without forgetting previously learned knowledge. It is particularly relevant in scenarios where data distribution evolves, new classes or concepts emerge, or the model needs to adapt to changing conditions. Continual learning techniques aim to address issues like catastrophic forgetting and adapt the model's knowledge incrementally. 6. Ethics and bias. As machine learning models have the potential to impact individuals and society, ethical considerations and addressing biases are of utmost importance. Ethical machine learning involves ensuring fairness, accountability, and transparency in the development and deployment of models. It includes addressing issues like algorithmic bias, privacy protection, data security, and the responsible use of AI systems. Efforts are being made to develop frameworks, guidelines, and regulations to promote ethical practices in machine learning. These concepts and considerations shed light on the various aspects and challenges involved in machine learning. By understanding these concepts, practitioners can make informed decisions, build robust models, and ensure responsible and ethical use of machine learning technologies. In next video, we will discuss about types of machine learning. Thanks for watching. Please like, share and subscribe.